lecture 11. So this is what we did last time, finding the confidence interval of the mean from the sample. And we were using the z critical value. And we have this formula for the confidence interval. The formula for the confidence interval is something like this. And we just put in everything, and the result was that with 95 confidence level, we were able to say that the mean value of the pumpkin weight is between 20.76 to 23.24 with 95% confidence. That's what we had. Okay. Now, I also explained that from our Python experiments that we ran last time, I showed you how if your original population is not normally distributed, and if your sample size is not too big, then your mean value wouldn't be following a normal distribution, right? But if you have more and more samples, then the mean value does follow normal distribution. That's another thing that we did yesterday in the last lecture. Okay, so here's what happens when your sample size is small. Okay, so when sample size is small, there are two problems. One is your original population distribution may not be normal, and the mean value wouldn't be following a normal distribution, which is not good. Because if it's not, then we have little idea of what to do. But if the population, so in the experiment we ran yesterday, we had this M-shaped distribution for the population, right? And when we had small sample sizes, the resulting mean value didn't look like normal. However, if the original population is not exactly normal, but somewhat normal, somewhat bell-shaped, in that case, the mean values of small sample sizes still follow normal distribution. So that will be our assumption in all of our estimations that we do afterwards. So we're going to assume that at least the population distribution is approximately normally distributed, so that when you take the mean values of the sample, it is very close to a normal distribution. Now, still, another problem that we have is that for small sample sizes, the sample standard deviation, which we denote as S sub x, that won't be a good enough approximation to sigma, the population standard deviation. Now, unless for some reason we know the sigma, in very rare circumstances, we may have an access to sigma, but that's really rare. So to solve this problem of not knowing the population standard deviation, there was a person who was writing in a pseudonym of student that made this new kind of distribution that gave us a better idea of what to do, and that's called the student's t distribution, or just t distribution. Okay, so let me explain what this is about. So we're assuming that the population is approximately normal, and the sample size is less than 30, so that using the normal distribution to find the confidence interval for the mean is not trustworthy. And let's also say that the sigma is not known. In such a case, what we do is we use this t distribution, and if you compare the t distribution with the standard normal distribution, the t distribution is wider. So that if you think about the 95% area uh, or 95% confidence level, in the standard normal distribution, you would see about here to here is 95%, but then if you go to the t-distribution, the 95% area would be wider, right? You would have a wider interval if you want to cover 95% if your distribution is wider. Does that make sense? Okay, yeah. Wider distribution means your confidence interval will end up being wider. That's what I wanted to say, okay? In other words, there's more uncertainty. See, because you don't know the population standard deviation and you're substituting your population standard deviation by your sample standard deviation, you have to take account of the fact that you don't know everything. You don't have the full information. And that makes it harder for you to estimate the mean, okay? Or to come up with the confidence interval. All right. So how do we then calculate the confidence interval for the t-distribution? Well, the t-distribution is dependent on this number called degrees of freedom. It's called df. The smaller the df is, the wider the distribution will be. And you kind of understand why, right? The less sample you play with, there's more uncertainty, so you're going to have a wider curve. So for the normal curve, you just need two things, the standard deviation and the mean value. And in fact, if you have the mean value as 0 and standard deviation as 1, you just have a single curve, the standard normal distribution curve. That's the only one thing that you use. However, if you go to the t-distribution, you have different curves depending on this number df, the degrees of freedom. And the degrees of freedom means how many values are truly free. Now, here you do n minus 1 because out of the n samples that you pick, you're using the value of the sample standard deviation, Sx, right? The sample standard deviation is calculated from the sample. And because that's used as a data point, if that number is fixed, then the other numbers lose 1 degree of freedom because you want to fix that Sx. So that's like, it's a bit hard to explain, but this concept of degrees of freedom comes up a lot. Later on, we're going to see that for linear regression analysis, we need the degrees of freedom to be n minus 2 because over there we use 2 values estimated from the sample as a parameter to plug in. So if you use up some information from your data as a replacement for the estimation, you lose that much degree of freedom. That's basically the idea, right? But if that explanation is not sufficient for you, just remember for t-distribution, it's always df equals to n minus 1. So you don't have to fully understand how this is, but just remember degrees of freedom is always n minus 1 when you do the t-distribution. Okay. And then for the critical value of t, or t alpha over 2, here, instead of using inverse norm, you use inverse t. And it's the same thing, 1 minus alpha over 2, but except you need to provide the degrees of freedom because the curve changes with the degrees of freedom. So that's the difference. And the confidence interval formula is exactly same as the case when we do the normal. The only difference is now you use a t alpha over 2 rather than z alpha over 2. All right, so it's these steps that we follow. So let's try to do the following example to see what this is about. Okay. So a farm is selling pumpkins, and a buyer wants to know the mean weight of the pumpkin they are selling. So the buyer bought first 10 pumpkins and calculated the mean. and variance to be 22 pounds and 4 pounds. Find the 95% confidence interval for the mean. Now, notice that this question is exactly the question I did yesterday, which I showed you in the beginning of these slides, except the only change is that before I had 40, but this time we only have 10 pumpkins, okay? So with only 10 samples, how confident can you be about your population mean? Okay, of course, the end result should be an answer that has bigger interval than before, right? You would end up with something bigger. So our goal is to actually calculate this and come up with the answer. All right. Okay. So so what we can do is say that alpha, the significance level, is 1 minus the confidence level. So that's 1 minus 0.95, which is 0.05, right? And then we go to the calculator to do the inverse norm, inverse t. And you can go to second vars and go to inverse t. I noticed that TI-82 doesn't have inverse t. So in that case, you'll have to use the table. I'll show you how to use the table to get the same result. Okay. All right, so what you do is the area that you have is 1 minus, 1 minus 0.05 divided by 2, right? And then you put the degrees of freedom. What's the degree of freedom here? Oh, I should have said that. Degrees of freedom is n minus 1, right? And what's that? What's n here? 10 minus 1, so that's 9, right? So that's the number that you have to put in. So I put 9 as the degrees of freedom. You paste it, and you get 2.2621, okay? Or 2.2622. Or let's just say 2.262. So that tells us that T, T alpha over 2 is 1 minus, 2.262. And we obtain this by doing inverse T of 1 minus 0.05 divided by 2 with degrees of freedom 9. No. 0.05 divided by 2, comma 9. Okay. So that's what we got. And then now you write down this, we just calculate this formula here, which is this one. So we're going to use this with x bar being, the sample mean is 22. So I put here 22. As well. T alpha over 2, we just found out to be 2.262. So I'm going to replace that by 2.262. And sample standard deviation is 4. Put that as 4 here. And square root of n is equal to 10. Okay. So let's do this. I'm going to calculate 2.262 times 4 over square root of n and add and subtract it from 22. Okay. So let's see, 2.262 times 4 divided by square root of 10, 2.86. So let's add and subtract. So 22 minus 2.86 and 22 plus 2.86. And you get that 19.14 through 24.86. So 19.14, I should have said 19.14 u 24.76. You see, 86. All right. So we know that the sample mean, the population mean is somewhere between here and here. Now, if you compare this with the previous answer, you see that it was 20.76 to 23.24. So when we had more samples, we are more confident where the sample mean was, and the population mean was, right? Here, because we have less samples, we have less certainty. Okay, so it can vary more. Right? So that's how we use this. Now, I promised that you can also do this with the table. So I handed out this table yesterday. Is there anybody who don't have this? You need this? Okay. You need this? Don't you have this yet from yesterday? Okay. All right. So you don't have it? You need this? Okay. So the using the t distribution table I handed out yesterday. Look at the degrees of freedom 9. So I see the degrees of freedom 9 right here, right? And when you do confidence interval, so I didn't explain what two-tailed test and one-tailed test is because we haven't done any hypothesis testing yet. But see, when we do confidence interval, you end up putting bars in both sides, two sides, right? So that corresponds to a two-tailed test. So in a two-tailed test with degrees freedom 9, you see that 5% significance level. Remember that significance level is the 1 minus the confidence level. So confidence level 95% is same as significance level 5%. And if you look at where the 5% and 9 meets, you see 2.262, exactly the value that we used before, right? So that's how you use this table to do it. Okay. So you can figure out your T alpha over 2, the critical value of the T distribution, either using the inverse T on your calculator or using this table. Okay. So you can use either one, whichever you think is easier. Just go with that. All right. So now let's talk about margin of error. The number that we just calculated and added or subtracted is called the margin of error because it's like the difference between the true average, true population mean, and your estimation. So at least one of the lower estimate or the upper estimate will be closer to the population mean with the less than this margin of error, right? So it's like margin of error is like the radius of the confidence interval. That's what it is. And sometimes you're interested in this quantity because you might want to know, or you might want to reduce that margin of error. If the margin of error is too big, you might think, oh, that's no good. We have to increase the sample size because the more samples you have, the margin of error will decrease because there's more certainty, right? So that will be another thing that we consider. Okay. And if you use this margin of error, then the confidence interval is a lot easier to write. Okay. Now notice that sometimes I use strictly greater or greater or equal to. I think the strictly greater is the correct one, but it doesn't really matter in a continuous one. So either one should be okay. All right. So let me show you another example using the t distribution. Here, there's a slight curveball here because instead of giving you the uh, sample standard deviation, I just give you the uh, sum of the difference squares. Okay, so this is called sum of squares. So let's say we obtain this sample. How many numbers do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 samples. Okay, and from those, you can plug that into your calculator, do one variable statistics, and find the standard deviation of the sample and the mean value. Or you can just use these two quantities. And the question is to find the confidence interval with 90% confidence level. All right, so first, if you're looking for 90% confidence, you do 1 minus alpha equal to 0.9. By the way, this is exactly on your handout, so maybe it's better to look at your handout and put additional notes there. Okay, so you have less writing. Okay. All right, so you have 1 minus alpha equal to 0.9 because alpha is the significance level. So the significance level is 10%. And therefore, we're looking for the critical value, t 0.1 over 2. And by the way, what this means is this 0.05 is, if you have the normal curve and you have the confidence interval, then there's the region at this tail, there's this right tail and the left tail. And these two have to add up to 10%. So one side will be just 0.05. That's what this 0.05 means, okay? Because one side will be 5%. So that's what we have, what we want, t of 0.05. But of course, before we use the inverse t, we better have the sample size and degrees of freedom. So since we counted the samples to be 12, we know that the sample size is 12 minus 1, which is 11. Right? So now we're ready to calculate. So what do we do? Okay. We can do second vars inverse t, then enter. And this time instead of 1 minus 0.05 over 2, this is the alpha value, right? So we're going to delete this one and just put in 0.1. That's alpha. Okay. And the degrees of freedom is now 11 because 12 minus 1. So we paste it and we get 1.795 or 1.796. Okay. So I wrote it as 1.7959. Okay. Yes. What did I do? Oh, that's wrong. If I said the inverse norm on the paper, please correct it. So the question is, what's the difference between inverse norm and inverse t? When do you use inverse t and when do you use inverse norm? Can anyone answer? When do you use inverse t and when do you use inverse norm? Yes.
Inverse t when you have less than 30 samples.
Yeah, inverse t when you have less than 30 samples. Right? Because if you have less than 30 samples and you don't know the population standard deviation, okay? If both conditions are met, then we use inverse t. Okay. Yeah. Yeah. So in the handout, I actually spelled that out, right? It says in the title when population standard deviation is not known and sample size is less than 30? Did you find it in your handout? I just read it for you. When population standard deviation is not known and sample size is less than 30. It's on the top. Do you see it? Okay. That's when you use inverse t. So we're using inverse t, so it's 1.7959. All right. And then what do you do with sample standard deviation? Of course, you can just punch in all these numbers and calculate the Sx, but since this is given, we can calculate Sx using this way. Remember, the Bessel corrected one is you divide it not by n, but by n minus 1, right? And the Bessel's correction n minus 1 is also from the fact that you're using the mean value of the sample to estimate the standard deviation, and that's why you lose 1 degree of freedom. So here in the Bessel correction, this n minus 1 is actually another place where you see the degrees of freedom. I just didn't explain it to you there. So there are many places where you see the degrees of freedom. But let's just take this as a formula. This is the formula for Sx, and you compute this, and you get 13.2425. Okay. Okay, so we have the sample standard deviation. We get the critical value for t. Now we can calculate the margin of error, right? And I did everything here. And if you do the calculation, this is the final answer. So it's pretty straightforward, right? Okay. Any questions? All right. Since it's on the handout, I'll just move on. Let's see. This shouldn't be there. Okay. All right. When population standard deviation is known, okay, when population standard deviation is known, what do you do? In that case, since sigma is known to us, there is less uncertainty, and you can just use the normal distribution. So even if the sample size is less than 30, if you know the population standard deviation, your margin of error is just this. You don't have to use the t distribution. Okay. But in practice, this rarely happens. Like it's rare that you know the population standard deviation before taking the sample. Okay, and number 3, when population standard deviation is not known, but the number of the sample or the sample size is more than 30 or more. In that case, you just use the normal distribution. Okay. Now, there is one more thing I want to say here. In this case 3, I wrote this as z means the z-score, which means you use the normal distribution. You use inverse norm to calculate. But here you can actually use the t distribution if you want to. Except that for t distribution, you have to type in the degrees of freedom, so there's more work. And in some sense, using the t distribution is better because the rule of the thumb for saying, well, starting from 30, let's just use normal distribution, is because at that point, the t distribution becomes more and more like the normal distribution. So at some point, they are not distinguishable. It's basically they're off by like 0.001 or something. So it doesn't really change much. Okay. So if in doubt, you can just use the t distribution. Yeah. In most cases, yeah. And it's not gonna change much. All right. So let me give you examples from 2 and 3. Okay. So it's pretty much the same question as before, but the difference is now your population standard deviation is given to you. Okay. And that's the second case I talked about, right? The second case. When population standard deviation is known, you can just use the normal distribution. So we first calculate the z alpha over 2 by the usual inverse norm. Uh, so let's do this. Since alpha is 0.1, it's the same story. So turn this on. Second vars, inverse norm. And you need 1 minus zero point 0, no, 0.1, sorry, 0.1 divided by 2. Enter. And you get the value 1.6449. So that, oh, why did, okay. So you get that. You have a question? Yes.
So, it can does it have to be both of them when we have to use the distribution? Like, you know how the sample size is less than 30?
So the sample size is still less than 30, but the difference here is that you know the population standard deviation.
So that's enough to.
In that case, you use the normal distribution. Okay. So you have to remember there are 3 cases. Okay. Yeah. Or you might even simplify this as 2 cases. If you know the population standard deviation, then go with the normal. If you don't know, you just go with the t distribution. Yeah. But if the sample size is 30 or more, then you have a freedom to choose either one. Yeah. Okay. So I'm using the normal distribution here, and I calculate the margin of error just by plugging the numbers here. And I add and subtract to the mean, and here's the answer. And the answer here will be slightly different because you know the population deviation 14. Before it was our distribution was in the previous question. It was 13.24, so it's smaller. Right. Okay, second example. A survey of 40 students in a college showed that the amount they spend on video games annually is an average of 13.50 with sample standard deviation of $7.25. What do you think? Is that like an overestimate or underestimate? I think this was collected before there was Steam. Do you think so? Yeah, right. Yeah, after Steam, everybody's spending like $30 or more. Okay. Anyways, what is the confidence interval with confidence level 95% for the average video game spending for the entire student body of 6,000 students? Okay. So this time the number of sample size is 40. So we can use the normal distribution. And, see if you get a similar answer if you use the t distribution. Okay. What's the question? So like between 40, why is it there after the greater than or less than 30? Like it's 30 after. Yeah. Okay. So why is 30 like a critical point where you change from t distribution to the normal distribution? Actually, it's just some tradition. Uh, it was done like long time ago. T distribution was considered hard to calculate because we didn't have like handheld calculators. Okay, so these T distribution, these are like 100 years old. Back then they didn't have a calculator, so they only had a table. And yeah, and then because T distribution was changing with the degrees of freedom, it was harder to have all the values. Whereas normal distribution, you just have one thing, so it's easier to use. So that was always a question like, when can we just use the normal rather than using the t? Right? Nowadays, that distinction is really not there because like using the t distribution is only just one more step than the normal distribution. So actually, our textbook that we adopted for this one, says just use t-distribution all the time. Yeah. So that's something. But I'll just use the normal distribution. So I can use the inverse norm and I get 1.96, and then I get the error, add and subtract. So you kind of see that uh, now everything is somewhat similar, right? You just find the critical value by inverse norm or inverse t, calculate the margin of error, and add and subtract that to the mean value, and that's your confidence interval. And you kind of know where the median is, the mean value is. So we know that the mean value is somewhere between $11.25 to $15.75. Uh, okay, but that's like not a good number. Like if you want to publish a newspaper, you want to say, oh, average student spends about $13. You want to say something like that, right? But your confidence interval is too wide. This is too large. So in that case, a second thing is of interest, and this is actually pretty important. So I want you to think about the following thing. Uh, yeah. So if you're kind of tired now because you're seeing mostly the same thing, please pay attention to this one because this is somewhat different and it's important. Okay. And it's actually one of the places where if such a question is on the exam, usually most people get it because it's easier. It's just the type of question where you just plug in the numbers and you get some answer. Okay. All right. So here's a problem. I don't like the fact that this confidence interval is so too large. The margin of error is $2.25. That's unacceptably too large. And let's say the publisher of the newspaper who wants to publish this says, okay, we need to increase the sample. I need this to go down to 1. And look, if you have more samples, certainly z alpha over 2 is not going to change if you fix the confidence level. The sample standard deviation may change a little bit, but we don't know if it's going to go up or not. So we're going to say that it's about the same. What really does change is this n, which is sample size. And you can see that the bigger that n is, the smaller the margin of error would be. And it makes sense because the more samples you have, the more confidence you would have, which would narrow the confidence interval. Right? You get this idea, right? So now the question is reversed, and the question that we pose is, in the previous example, if we want to estimate the mean with error less than $1, how many samples do we need? Okay, and the formula is this: the size required to have certain margin of error, where this e down here is the margin of error, right? Is this formula. You just plug everything to this formula, and that's the answer. And for us, since we don't have the sigma, we use the 7.25, the sample standard deviation. So we use the 7.25 and 1.96, same as we before. See, we use the 1.96 here, 7.25, same as before. But instead of dividing by the square root of n, now you divide by e, and because we want the e to be 1, we divide, square everything, and the result is 201.92. But that's another problem. You can't have 201.92 students. You can't take a student and then cut him or something. That's gross. All right, sorry, but you see my point. You can't have a fractional person. That's not allowed, right? So what do? You need to have a whole person. So you always have to round up. Okay, you see the point? You always have to round up. You cannot round down. Okay, for questions of how many samples do you need, you always have to round up. Okay, so you have to round up, and if you round up, you see that we need 202 people. And if that's reported, then the publisher will say, okay, we need 202 samples. So go out there, get me 162 more people so that now I have 40 plus 162, so that's 202. So all is good. Okay. All right. So Uh, so that's how we do this. Okay. But now I still want to talk about where we get this formula from. So this formula right here, n equals to this strange formula. Well, unfortunately, I'm not going to give you that formula. Or maybe, if I feel nice, I might give you. But most likely, I'm not going to give you that formula. Why? Because that's something you can calculate from the margin of error. So here's the margin of error formula, which will be given as a formula sheet. Okay. But let's say you wanted to know what n is. That means you just have to take this as an equation and you have to solve for n. And that's just algebra. You should be able to solve for n. Okay. So let's see how we can solve for n. Right. So first, when I see a fraction, the first response for me is to get rid of the fraction. So I just multiply square root of n both sides. And if this square root of n goes to the left side and it gets multiplied, I don't see the square root of n anymore. Okay. So I have this. It's nice, right? Now, our goal is to isolate n. Isn't that right? So what should we do? To isolate n, we better first get rid of, huh? You should get rid of e, right? So you divide by e. Yeah. Now, if you divide by e, uh, so basically what's happening is the square root of n and e is switching places. Okay. And now to isolate n, you just have to get rid of the square root. What gets rid of square root? You square it. So if you square it, that's the formula. Okay. So that's easy, right? Yeah. Everyone here should be able to do that. Okay. So that's where this formula uh, appears. That's how you get this formula. And this tells you that if you know the standard deviation or have some idea of the standard deviation, and you also know the critical value, and if you have a desired margin of error, then this formula will tell you how many sample size you would need in order to successfully narrow down your confidence interval that's good enough to use, right?